We will start our discussion today with what is known as the balanced sliding window protocol. So, this is a protocol which is followed at the very lower layers of the network stack to achieve reliable communication among two nodes which are communicating with an unreliable channel. So, we will start with a few definitions. Two processes P and Q, each will send an infinite array of words to the other. So, it is a stream of words that each has to send to the other side. For process P, we have the following definitions. In P is an infinite array of words to be sent to process Q. Similarly, in Q, for process Q, in Q is an infinite array of words to be sent to process P. Out P is an infinite array of words being received from process Q. Initially, for all I, out Pi is undefined, because initially at the beginning of the protocol nothing has been received from the other side. So, all the entries of out P are undefined, and then as and when words are received from the process Q, they are written into the array out P. Okay. When the ith word is received from process Q, it is written in out Pi, okay, and so on. SP denotes the lowest numbered word that P still expects to receive from Q. Now, we are talking about sending an infinite array of words, right. So, there we assume that these words are indexed. So, P has an infinite array of words to be sent to Q, and these words are in P0, in P1, in P2, in P3 and so on. Okay. So, this is the array of words that has to be sent. So, in P0 has to be copied to out Q0 after the transmission is over. Okay. Is it clear? And SP denotes the lowest number word that P still expects to receive from Q. Okay. Remember that words can come out of order, even if they are sent in a proper sequence, they can be received out of order. So, it is quite possible that some out Pk has been received, but some words before that may not have been received, right. So, at any time P has already written the words out P0 through out P SP minus 1. Why? Because SP is the lowest numbered word that P still expects to receive from Q. So, all indexes less than SP, for them the out P is already filled. Okay. So, to show this thing through a picture, this is how it is going to look like. That this is the array in P for P, this is the array out P for P. These are the words that has to be sent to Q. This infinite array of words has to be sent to Q, and these are the words that has been received from Q. Okay. And SP, as you can see here, denotes the first word that is not yet received from Q. All right. There can be some other words like these two which are already received, but these two has not been received yet, right. Do you follow? Okay. Now, we will see that how the two processes, how they progressively send these words, and these words themselves, when a word is sent, it automatically works as an acknowledgement for some word sent by Q. Okay. So, we will see that a word sent by P can act as an acknowledgement of a word sent by Q and vice versa. Okay. So, we will see how that is achieved. So, we require two properties in this protocol. The first requirement is that we should have safe delivery. That is, in every reachable configuration of the protocol, out p 0 through sp minus 1 should be equal to in q 0 through sp minus 1. What is out p 0 through sp minus 1? The sequence of words that has already been written, right, and these words that has been written by p in its incoming array should be actually equal to the array in q 0 through sp minus 1, because those were what were sent by q. Okay, so this indicates that the packets that were received are actually the packets that were sent by q. Similarly, the reverse has to happen also, that is out q 0 through sq minus 1 should be equal to in p 0 through sq minus 1. Okay. And then we have eventual delivery, which says that for every integer k greater than 0, a configuration with sp greater than or equal to k and sq greater than or equal to k is eventually reached. Now, this makes sure, this requirement indicates that there has to be progress, that you cannot end up keeping on sending and receiving the same set of packets and not moving forward. Okay. So, you have to move forward in that array. So, you will have to finish off some of the words and then start sending the next few words, right. Now, this is the protocol. The protocol goes like this, that the packet, we will define the packet as pack to indicate that it is a packet, and then two numbers w comma I. This transmits the word w equal to in pi to q. Okay. So, w is the word that is being transmitted, the packet, the data that is being transmitted. I is the index of that word in the array in pi. Okay. So, the ith word in pi is w. Okay. And when we say pack wi is being sent, we mean that the ith word of in p, which is w, is being sent in this packet. Clear? The processes use constants LP and LQ as follows. Okay. LP and LQ have the constraint that both of them cannot be 0 and they are both positive. So, LP plus LQ is greater than 0. Okay. Now, these constants are used like this. Process P can send the word w equal to in pi as the packet this thing only after storing all the words out p 0 through out p I minus LP. Now, look at this thing very carefully. I am receiving words from q, okay, and storing them in out p. The process P is receiving words from q and storing it in out p. The process is sending words from in p. Okay. We are not going to allow the process to send words from in p unless certain number of words have been received in out p. Okay. So, that is why we say that it is balanced, it is a balanced protocol. We are not going to allow sending of the words from in p arbitrarily fast. It is going to be synchronized in some way with the words that are received with from out p, okay, from q. So, how is that synchronization taking place? We are saying that process P is allowed to send the word in pi only when it has received all words from out p 0 through out p I minus LP, where LP is a parameter. Okay. LP is a constant. We will choose the value of LP for the protocol. Okay. Suppose LP is 5, then we say that you can send the word in pi provided that you have received all words from out p 0 through out p I minus 5. Okay. Then you are going to allow the sending of this word. So, that means that I is less than SP plus LP. Why? Because SP is the minimum numbered word which has not yet been received, right. So, you will only allow a word I to be sent if all words from out P0 through out P I minus LP is already there, right. What is the maximum value that this can take? This I? See, all words from out P0 through out P I minus LP should be received, right. So, I minus LP can at most be SP minus 1, right. So, I minus LP is less than or equal to SP minus 1, right. So, I is less than SP plus LP, clear? Is that clear? Because the word SP has not yet been received. So, all that has been received is out P0 through out P SP minus 1. So, I minus LP is less than or equal to SP minus 1, right. So, now if you change sides, if you take LP to the other side of the inequality, you get I is less than SP plus LP. I is less than or equal to SP plus LP minus 1. So, the I is less than SP plus LP, clear. When P receives pack WI, retransmission of words from in P0 through in P I minus LQ is no longer necessary. Why? Now, see, this could have been sent from Q provided that all words from out Q0 through out Q I minus LQ has already been received. So, what is out Q0 through out Q I minus LQ? The words in P0 through in P I minus LQ have been received there. Okay. So, these ones need not be sent, right. So, see that what is happening here is that this packet pack WI received from Q is acting as an acknowledgement for all packets in P0 through in P I minus LQ. This is acting as an acknowledgement for that. Okay. Now, is this absolutely clear, or do you have any questions about this? Can we go ahead? Okay. Now, let us look at this picture once again. We will maintain a variable AP. AP will indicate the first packet that still needs to be sent. Okay. All right. Now, whenever we receive a packet like here, we know that from in P0 through in P I minus LQ we need not send. So, if AP was less than I minus LQ, we will update AP to I minus LQ plus 1, right, because we know that these need not be sent anymore. So, we will update AP like that. So, AP is a variable which will be updated by the protocol, and it will always point to the minimum word which still has to be sent to Q. Okay. And then this is SP plus LP. The word that we cannot still send is SP plus LP. Why? Because we can send only those packets I, we can send a packet I provided that I is less than SP plus LP, right. So, therefore, we can send all packets in this window. We can send packets in the window AP through SP plus LP minus 1. This is the window from which we can send packets. We need not send any packets before this because they are already acknowledged to be received, and we are not allowed to send packets after this by virtue of the protocol. Okay. And on the receiving side, SP is the one which indicates the lowest numbered packet not yet received from queue. Okay. And the window closes at the maximum numbered word which has already been received, right. Now you see this window cannot also be arbitrary. Why? Because the sending window here is fixed, right. The sending window here is within certain range. So the receiving window here cannot expect that some packet here will be received, several words down the line. It cannot come before because this window is also has a limited size, right. Is that clear? So what's happening here is that as the words are getting received, so when some word here gets received, then again this word gets received, then SP will move here. When these two words are received, then SP will move here, right. So this window will slide like this. Similarly, when some word here is received, then since whenever SP moves, this SP plus LP will also move. So we will have more packets to send. Now when those packets are sent, and then more packets will be sent from this side. So the windows will slide. These windows will slide along these arrays, right. They will slide along this array, okay, and that is why we call this the sliding window protocol. Yes.
So when does the AP move ahead? When the acknowledgement is received or when it has transmitted?
When some packet is received.
AP, sir.
Yeah, when some packet is received by P, yes, it checks this thing. It knows that in P0 through in P I minus LQ is no longer necessary. If it finds that AP is less than I minus LQ, then it will update AP to I minus LQ plus 1. Let us look at the protocol definition now. Let us look at the statement of the protocol.
So you assume that P knows LQ.
Yes. LP and LQ, these parameters are known to both sides. Okay. This is the statement of the protocol. So the protocol, remember I said that distributed algorithms are specified in terms of a precondition, action and postcondition kind of thing. So here for this protocol there are three different actions: SP, RP and LP. Okay. Similarly for the queue, process queue, it will be SQ, RQ and LQ. Okay. Now what is the action of SP? When you have a packet I which is such that AP is less than or equal to I and I is less than SP plus LP, what is this window? This window is this window, okay, that it is less than or equal to I is AP is less than or equal to I, and this is less than SP plus LP. Okay. Then we send packet this thing to Q, packet in PI I to Q. This action is the sending of packets in this window, right. It may send all the packets also, it may send some of the packets, but it is going to send this, do this action infinitely often, right. What does RP do? RP is the receiving of a packet. So when it receives a packet WI from QP, QP is the input Q, this QP is the set of packets that it is receiving from Q. So when it gets this packet from the Q, it will receive the pack Wi, then it is going to check is out Pi is undefined. If it is not undefined, then this packet is a retransmission, it is receiving it for the second time, then it will ignore. But if it is undefined, then this packet is being received for the first time. If it is being received for the first time, we will first receive it. So, we will write out Pi is equal to W, then we will do the following thing. Note this thing very carefully. We will update AP to the max of the present value of AP and I minus LQ plus 1. Why? Because the fact that this packet is received here is acknowledging that all packets from in P0 through in P I minus LQ has already been received. Okay, that is why that packet was allowed to be sent, right. So, therefore, we need not send any packets from in P0 through in P I minus LQ plus 1 anymore, right. So, therefore, AP is updated to the max of the present value of AP and this. So, this is how AP is updated, right, and as you can see that AP can only move towards the right because we are taking a max, okay. And also we do SP, we recompute SP to be the minimum J such that out P J is undefined, right. So, suppose this packet is received, then SP is going to move here, and then when this packet is received, SP will move here, right. So, SP is also going to move towards the right, it is going to increase only, except that the increment may not be by 1 always, right, okay. And for every packet, SP may not increase also. For example, if the packet received was this one, then SP will still remain here, okay, right. So, we are just recomputing SP to be the minimum J such that out P J is undefined, clear, right. And the third thing is that whenever you receive a packet, then that packet has to be taken off the queue. So, this is just this action just does that, it does QP equal to QP minus, this is the set minus operation, and the packet WI, okay, this is taking the packet off the queue, right. So, this is the protocol. Now, what we have to prove in this protocol is that this protocol satisfies those two requirements that we mentioned before. One requirement was that the packets will be safely delivered, and the second requirement was that they will eventually be delivered. So, there will be progress, right, there will be progress in delivering the packets, right. Now, to show that there is going to be progress, what we need to establish is that this SP and SQ, they will continuously increase, right. First thing that we need to show is that the protocol will not deadlock. So, there will be no configuration under which P will not be allowed to send any packets, Q will not be allowed to send any packets, this will not happen. We must first prove that at any point of time either P will have a packet to send or Q will have a packet to send, right. That way we will show that the protocol is not going to deadlock anywhere. Then we will show that if the protocol does not deadlock, then the packets will eventually start arriving and SP and SQ will keep on increasing, right. So, we will start proving these aspects of the protocol, okay. We will start by looking at what is called a protocol invariant. Now, what is an invariant? An invariant is a property which holds throughout the lifetime of the protocol. So, when we say that this is an invariant, it means that this property will always hold in all states of the protocol. Okay. We prove the invariant and then we use the invariant to prove the correctness and the results that we wanted to prove about the protocol. So, let us start looking at the steps, the different clauses of this invariant. The first one says that for all I less than SP, out Pi is not undefined. Okay. Now, how do we show this? So, for proving invariants, what we do is we look at the initial state of the protocol and then show that every action, assuming that invariant holds before the action is taken, we will show that the invariant holds after the action is taken, right, throughout the protocol. That will guarantee that the invariant holds always. So, let me reiterate. To prove the invariant, we first prove that the invariant holds in the initial state of the protocol. Then we show that if at any state of the protocol the invariant holds, then the actions, the three actions that we saw, LP, RP and SP, they are not going to change the invariant, they are going to preserve the invariant, right. That way we will prove that the invariant holds in all states of the protocol, right. Now, what is the initial state of our protocol? In the initial state of our protocol, what is the value of AP? 0. What is the value of SP? 0. What is the value of out Pi from 0 through infinity? Undefined. The whole out P array is undefined, right. What is the value of the LP and LQ? They are given constants, right. So, in P is totally full, AP is at the beginning of the in P array, out P is totally undefined, SP is at the beginning of out P, right, and both the queues are empty, right. This is the initial state of the protocol, right. Now, in that state of the protocol, for all I less than SP, out Pi not equal to undefined vacuously holds, because there is no I less than SP, right. Now, suppose that in some state of the protocol this thing holds, right, then we will have to show that each of these actions does not change it, right. So, let us look at sending. Well, sending does not affect out Pi at all, it does not affect out Pi at all, it does not affect SP also. So, that is not going to be affected, the invariant is not going to be affected by SP, right. Similarly, it is not going to be affected by LP, because it does not change out P, it does not change SP. Now, RP changes both out P and SP. How? When it gets some packet I and finds out Pi is undefined, then it sets out Pi equal to W, okay, and then it recomputes SP to be the minimum j such that out Pj is equal to undefined. So, by virtue of this recomputation, we are again guaranteeing that for all I less than SP, out Pj for out Pi is not undefined? Because we have redefined SP to be that. We have redefined SP to be the minimum j such that out Pj is undefined. So, for all j for all I which is less than this SP, out Pi is not undefined, right. So, that means that this still holds. Is it clear? Yes. See, it is very simple. All I am trying to say here is that we are trying to show that for all I less than SP, out Pi is not undefined. For all I less than SP, out Pi is not undefined. And we are showing that this invariant, if it holds before any of those actions, will also hold after the action. Now, those actions which does not change SP and does not change out P, they are not going to affect the invariant. So, we rule out SP and LP. We are only concerned with RP, the action RP, because the action RP is the only one which affects SP and out P. Okay. But what are we doing in action RP? We are assigning SP to be the minimum j such that out Pj is equal to undefined. What does that mean? That for all I less than SP, out Pi is not undefined, right. So, therefore, at the end of applying RP, this will still hold. Okay. So, we have shown that this is an invariant, and by a similar reasoning we can show that this is also an invariant from the other side. Now, look at this one. This one says that, let me write this down. This one says that pack Wi belongs to QP implies W equal to in QI and I less than SQ . Now, this part, that if pack Wi belongs to QP and W equal to in QI implies W equal to in QI, this part is guaranteed by the sending, right, because what are we doing? We are when Q is sending a packet, then it is copying in QI into pack Wi and putting it in the queue, right. So, this is very straightforward, that if there is a packet in the queue, then it can only have been put in by the action SQ, and what has SQ done? SQ is going to copy in QI into the pack Wi and put it in the queue. So, this part is obvious. This part is also obvious because in queue only sends packets which are in the range of AQ less than or equal to I less than SQ plus LQ. So, you will see that in Q for the SQ action in Q, if this holds, then only the packet I is copied into the queue. Remember, by the definition of the protocol, we send packets only in this interval. So, therefore, if the packet is already sent, that means that this I is less than SQ plus LQ. However, we need to make sure that at the time of sending, of course, this was the case. At the time that the packet was sent, obviously I was less than SQ plus LQ, but we have to make sure that it remains true even after the packet was sent, because the packet is in the queue and it can take substantial amount of time for it to traverse along the queue, right. Now, to observe that it will hold also after the packet has been sent, we observe that look, SQ can only increase, SQ can only increase. By definition of the protocol, we only increment SQ, it can never decrease, and LQ is a constant. So, this side can only grow, and I for this packet is fixed. So, therefore, this inequality, if it was holding at the time the packet was being sent, will continue to hold even after the packet has been sent, right. Subsequently, after the packet has been sent, SQ can increase, but even the increased SQ plus LQ will be greater than this, because increasing this does not disturb this inequality, right. Is it clear? Yes or no? Let us look at the third thing here. Let us look at the third. So, we have looked at these four. This is symmetric to the previous one and can be proved by a similar reasoning. Now, let us look at this one. Out pi is not equal to undefined implies out pi equal to in qy and AP is greater than I minus LQ. Okay. Now, how do we prove this part, that out pi is not equal to undefined means out pi equal to in qy? Because how do we update out pi? We update out pi to W when we receive pack Wi. Okay. When we receive pack Wi, we update out pi to W, right. Now, the previous thing says that pack Wi can be in QP if and only if W is in pi, right. W is in qy, yes, W is in qy, okay. So, then that W is what we are copying here. So, out pi is equal to in qy. See, we have already proven this, and it is this packet which when received is updating out pi, right. So, we have already shown that W is in qy and then this W is copied to out pi. So, out pi is equal to in qy, right. This one is slightly more tricky. What are we trying to say here? We are saying that if out pi is not equal to undefined, then AP is greater than I minus LQ. Why? Yes, because see, because this packet has been received, okay, what does it indicate? It indicates that all packets I minus less than I minus LQ has been already received, right. So, these need not be sent, and as you can see that what RP does is RP it changes AP to max of AP to I minus LQ plus 1. So, whenever the packet I is received, AP is changed to something which is at least as large as I minus LQ plus 1. Okay. So, this is going to hold again, right, AP greater than I minus LQ, right, and the other ones, other actions, they do not change any of these variables. So, they do not affect this inequality, only RP affects this inequality, right, but then what RP does is it updates AP to be as large as I minus LQ plus 1. So, it is always greater than I minus LQ, right. Now, let us look at the last one. We want to check AP less than or equal to SQ. Now, what does AP, how is AP in RP? What do we do with AP? We take this to be max of AP Now, what can we say about SQ from this? Yes, right. So, SQ will be greater than I minus LQ, or see what does this tell us? It tells us that all packets from in P0 through in P I minus LQ has been received, right. So, this tells us that all packets from in P0 through in P I minus LQ has been received. So, that means that SQ is greater than I minus LQ, right. Okay. Which is, and so therefore, if we take this and we take that AP by virtue of this is greater than see what are we doing here? We are maximizing this with this, right. I mean between AP and I minus LQ plus 1 we are choosing the max, right, and we know that this I that we have received, I minus LQ that we have received, okay, just hold on. So, this implies that this I is less than SQ plus LQ. Okay. Why? Why is I is less than SQ plus LQ? Yeah, if we just transfer sides of this, then we get this. Okay. So, therefore, we can say that AP is less than or equal to SQ. How? See, what are we trying to show? We are trying to show that if this one was true before RP was executed, it will hold even after this has been. Now see, if this one does not change AP, then it is going to continue to hold, right. If it changes AP, what does AP become? It becomes I minus LQ plus 1, right. If AP becomes I minus LQ plus 1, then that is going to be less than or equal to SQ, because I minus LQ is less than SQ. So, I minus LQ plus 1, I minus LQ is less than SQ. So, I minus LQ plus 1 is less than or equal to SQ. So, if AP is updated, then this is what AP is going to become. So, it will become again less than or equal to SQ, right. So, if it was holding before RP was applied, then it is going to continue to hold after RP is applied. There are two cases. One case is AP is not updated, in which case it continues to hold. The second case is AP is updated to I minus LQ plus 1, and then also this holds, right. So, in both cases we have shown that this will hold, continue to hold, right. Now, note one thing is that SQ can change in between, but it can only change, it can only increase. So, if it increases, it does not affect this inequality, right. So, we have shown this one also. The other ones do not, the LP, the SP and LP, they do not change AP. So, they do not affect this inequality at all, clear. Okay. So, now what we have done so far is we have proved this inequality, and with that we want to prove the safety and liveness properties of the protocol. That is, we want to show that the protocol satisfies the requirement of safe delivery, and we will show that the protocol satisfies the requirement of eventual delivery, both of which are required for the correctness of the protocol. Okay. In the next class, we will look at the proofs of this safety and liveness. Thank you.